So hello students, welcome to the lecture 2, and in this particular lecture we would be saying that what is a current. Now many students find that this topic is little difficult or little tedious. They don't exactly understand this concept and they find that the topic of current electricity is a bit tough, because I had also gone through it, but now I will be explaining you this concept in much more simpler way. Okay. So just consider this is a particular setup that I had made. Okay, which has a fixed rod. Okay, this is a rod. You can consider a rod, and to the end of this rod, I had attached this north pole of a magnet. Okay, north pole of a magnet, and this north pole is fixed. It can't move here and there. Okay, but now I'm bringing a south pole of magnet close to the north pole, but the south pole is not fixed, so it can move here and there, maybe right, left, or maybe top, bottom. Anyhow it wants to move in any direction. Okay, but this north pole is fixed. Now, as soon as I bring in vicinity to the north pole, as soon as I bring the south pole in vicinity to the north pole, what will happen, or what will I see is this north pole will generate some magnetic field. Okay, so this magnetic field would be leaving the north pole and it will be coming towards south pole. Okay, and now what I will see is this magnetic field, and my observation would be the south pole would be moving towards north pole. So the movement of south pole is in this direction towards north pole, and then they get attached due to attraction. So at the end our result would be, so this is north pole and this get attached to south pole. So this is what our observation is. I hope you understood this concept, okay, or you got a little bit idea, because now I am going to relate this topic with some other topic. Okay, now we will move to the next page. Okay, now consider that here it is charge. Let's say it is a positive charge. Okay, so this is a positive charge and this is a negative charge. Now again, the same experiment which we done in earlier page, we are going to compare both of them. Now a positive charge will create an electric field which is leaving from positive charge. See, it is creating an electric field which is leaving from positive charge and it is coming towards negative charge. So this electric field is generated, due to which the electrons get attracted towards positive charge. And see, earlier the distance, let's say the distance was d, and now it has almost come very much closer to positive charge. Okay, but what we understand from this particular thing is that only electrons can move. Okay, only electrons can move, but positive charges are stationary. They cannot move here and there. That means what I'm trying to tell is that the positive charge which you are seeing over here, we can compare it to the north pole of the magnet, which I had set up in this particular experiment. Okay, since our north pole was not movable, but our south pole was movable in any random direction. Similarly here, our electrons, or basically the negative charge, or electrons, as I used the term electrons in earlier lecture, that means lecture 1. So this can move anywhere, but this positive charge is stationary. So that's what I wanted to tell you from this particular concept by comparing both two. Okay. Okay, so now just think that I'm applying some energy, let's say phi plus phi energy, or if you are actually it is like when we apply battery, but right now I don't want to relate you with volts, but I will give just short idea. Battery, that means, let's say if I'm applying plus 5 volts. Now I know that you might not be knowing what voltage is, but just remember this, or just assume that I am applying plus 5 volts and here I am applying minus 5 volts. Okay, just assume here I am applying minus 5 and here I am applying plus 5 volts, and this can be done with the help of battery. Just assume or just remember it, but right now we don't need this because we don't know what voltage is exactly at this point. So what I am considering is that, let's say I am applying 1, 2, 3, 4 as 5 charges over here. So these are 5 positive charges. Okay, just consider this, and here I am applying 1, 2, and similarly 5 negative charges over here. Let's say 5 negative charges. Okay, now what will happen is that let me just take it up. Okay, so now what will happen is that as soon as I apply this positive 5 charges here and negative 5 charges here, so at this point, say let's say at this particular point, this negative charge, okay, this negative charges will get stored or will get accumulated over here at this particular point. Okay, and then what will happen is that, let's say once it will get accumulated, so I will like to draw an atom. So consider that this is the atom, okay, and this is a, so this was the nucleus of atom, and this is an atom. So this is an electron, and now the same case will happen what I had explained in my earlier lecture about that cat's fur. You know, this electron, this negative charge and this electron, they will repel each other. So basically these two will repel each other, and due to which this electron from this particular atom will move out. Okay, and then again if there is some another atom present over here which has electron, now this will come over here and this gets moved out from this particular atom. So this goes on continuing further. Okay, but what I want to tell you is that now here the process would be very much quicker. That means the movement of electrons from this point to this point would be fast. Why? Because of two reasons. One, due to repulsion. See, this due to repulsion of this particular negative charge, repulsion of these negative charges, and due to attraction of these positive charges. Attraction of these positive charges. I hope you are getting me. The what we saw in the earlier lecture, that means in lecture 1, at the end of lecture 1 we saw that when we rub the iron rod to the cat's fur, and then when we touched to one conductor, so electrons was only moving because of one phenomenon, that was due to repulsion, because rod 1 has negative charges, and when we touch that to the conductor, okay, so this charge got accumulated over here, and then due to repulsion the electron was moving further and further and further. So that was the reason. But now here, let's say if the electron was moving with some x rate, let's say x rate or some x speed, now here the electron is moving with x by 2 speed. That means it is taking less time over here. Electrons are moving very quickly over here. Okay, I hope you are getting me. So now we will move on to the next page. Okay, so now what I wrote over here is, now if electrons are moving towards positive charge, see these electrons are moving towards positive charge, we can assume that same amount of positive charge is moving towards negative charge. That what does this line mean? And I want you all guys to think on it. Like, see, if this is electron, it is moving towards positive charge. So we can also assume that that one positive charge, that same amount of positive charge is moving towards negative charge, or basically over this side. But just think how. Why? Because this page is contradictory, or this particular sentence is contradictory to this particular line, because earlier I had said here that earlier what I told to you is that only electrons can move, positive charges are stationary. But now here in this page what I had wrote is that if electrons are moving towards positive charge, okay, that means this side, we can assume that some amount of positive charge, that same amount of positive charge is moving towards negative charge, that means over this side. Now these two statements are contradictory. Okay, they are exactly opposite of each other. So I want you all guys to think on it. Okay, I'm pausing the video. So let's get to the answer. Okay, so let me erase this first so that I can explain this concept in much better way. Okay, and then let me draw this draw the conductor over here. So this is a particular conductor or piece of wire, whatever it may be. Okay, and let's say this. Okay, so sorry, I will use some different color to show that this particular charges has accumulated at this particular place, and these are the atoms. Okay, 1, 2 and 3. Okay, and these are the electrons present in that atom. Okay, and these are the positive charges which has come from this -5 of energy. Okay, -5 energy, this has accumulated at this particular place. Now what will happen is that this particular electron which is accumulated over here, it will come over here, and due to repulsion between this negative charge and this electron, okay, this electron will move out. So it will move out and it will come somewhere over here. Okay, and it will move out, and it will create a vacant space for few seconds or for few time. Now what will happen is that this electron, see this electron, just a second. So this electron and this electron, now they will repel each other. Okay, they will repel each other, and now this electron will come out. Sorry, now this electron will come out. Let's say I'm using different color. This electron will come out, and due to this, now these two electrons will repel each other. Okay, are you understanding? Now these two electrons will repel each other, and due to which this electron comes out. Sorry, due to which these electrons comes out. Let's say I'm using some blue color. This electron will come out. So now let's try to analyze this case that we know that this particular, see this electron, and this electron, they are tending to move in this direction, but at the same time, if you can see, just a second, if you can see very clearly that, see, when they are moving out, they are also leaving some vacant spaces or some positivity of atom. That atom, this atom, sorry, we'll use different pen. So this, sorry, just a second. So at the same time, this atom is gaining positivity. That means, what I mean to say is, if this 1, 2 and 3, if these 3 electrons are moving in this direction, but at the same time, what we can see through the microscope is this, see, 1, 2 and 3. This three vacant space, or the I will consider it as positive charges, is also moving towards this side. That means over here. Are you understanding that what I'm trying to tell you with this particular sentence is that if electrons are moving towards positive charges, see, these electrons are moving towards positive charges, that means over here. We can also assume that same amount of positive charge is moving towards negative charge. See, that means same number of vacant space or positive charge in this case, because atom has gained positivity by losing one electron. That means same number of positive charges are moving towards this side. Okay. So in microscope we see electrons moving towards this side, but at the same time what we can see is that positive charge is also moving towards this side. And this positive charge or vacant space, so this positive charge or the vacant space which we see from microscope, or forget about microscope, okay, this positive charge moving towards negative charge, or basically what we term it as voltage or volt. Forget that, just consider negative charge. This particular phenomena or this particular thing is known as current. I hope you are getting me. So what is known as current is that see this 1, 2 and 3, this 3 positive charge is moving towards this 3 positive charge is moving towards this direction, that means negative voltage. I hope you are getting me. So this particular phenomenon is known as current. Okay, so we will move to the next page. Okay, so now what we end up having the conclusion is that current always move from higher potential to lower potential. See, in this case, we just move to the earlier page. So in this page, we are having positive charges. Okay, plus plus plus. That means this particular terminal has higher potential. Okay, higher potential. Why? Because it has plus 5 amount of charge. Okay, plus 5 amount of charge, and here it is having minus 5 amount of charge. So I can say it is at lower potential. And our current, as you saw over here, this was our current. Okay, this was a current. That means this particular thing, or this particular atom, or this particular vacant space, basically, it was moving in this direction. That means it was moving from higher potential to lower potential. Okay, higher potential to lower potential. So what we can say is that we can assume our current. So we can assume our current as a water. Why? Because water also moves from higher potential. So see, consider this is a dam. This is at higher potential. So this particular point is at higher potential. Okay, higher potential. And this particular point, this is the lower potential. Lower potential. And water flows in this direction. Water is flowing in this direction. Water will never ever flow. Water will never flow in this direction. Water will never flow in this direction. Okay, so it will never flow in this direction. That's what I wanted to tell you, that current, we can assume it as the analogy of water. That means water flowing from higher potential to lower potential. Now let's go in detailed way that what is the magnitude of a current. Okay, so for this we can assume a river. Okay, and we can take a cross-sectional area or cross-section of the river. Let's say if this is a river, and if I want to know the speed, let's say speed of the river, so how can I calculate the speed of river? So for that, what I can do is I will take some area. Let's say if I am taking this particular area, okay, from here, from this part, and let's say this part. So I am actually covering this particular area. Okay, I'm setting some device. Okay, let's say this device is over here and another device is over here. Okay, so this, let's assume that this is device 1. Forget what it is, just think, or just assume that this is these are the two devices which are used to measure the speed of the fluid. So I'm setting these two devices, and let's assume that if 10 liter of water is entering per second and 10 liter of water is going per second. Okay, so this is how we calculate the speed of water, by taking some area. Okay, so we had taken this area and then we had set those two devices and then we had calculated it. I'm not at all interested in calculation part. So what I want to tell you is that similarly over here, this is a conductor. Okay, just a second. Similarly over here, so this is a conductor. In conductor, we are also taking this area, as you can see over here. So we are assuming this area, cross-sectional area. Okay, and from that area, how much amount of charge is flowing? Positive charge, obviously. Positive charge is flowing in one particular second. So that is known as current. Okay, in proper scientific term. Okay, so what we saw over here, it was actually a kind of visualization or just a kind of thing to clear your concept that how current is generated or how current moves from which direction to which direction. But what I want to explain over here is the mathematical term. Okay, I hope you are getting me. A mathematical term that if there is a conductor means wire, conductor may be wire. Okay, wire which is made up of iron or copper, that doesn't matter, iron or copper. So we will take a cross sectional area of it, and then we will just see that how much amount of charge or positive charge is passing through it per second. So current, as you can see, this is the just a second. So this is the formula for current. This is the formula for current. Formula, or I will say magnitude of current. That means number of charge per second, number of charge passing through that particular area divided by T. So actual definition of current is this one: number of charge moving from a cross sectional area. Just a second. Number of charge moving from a cross sectional area per unit time is known as current, or this is my definition. A flow of positive charge is known as current, but I won't recommend you this definition because it is not that scientific, but this looks actually good in terms of science. Number of charge flowing from a cross sectional area per unit time is known as current, and flow of positive charge is known as current. Okay, and unit for charge is coulomb, and unit for time is seconds. Okay, so we can write 1 coulomb divided per second, which is also known as ampere or amp. Okay, so C by S is also known as ampere, and 1 coulomb is equals to 6.25 into 10 raised to 18 electrons. Okay, so this is a very huge number. 6.25, that means it is like just a second. So 6.25 into 10 raised to 18, that means you go on just taking one dot over here and just make one raised to power less, that means 10 raised to 17, then 625 into 10 raised to 16, go on like this. So you end up getting some huge number. So 1 coulomb is, you can remember this, 6.25 into 10 raised to 18 electrons. So conductor, basically a conductor passes, if it is a good conductor like iron and copper, it may pass more than 1 coulomb charge. That means it is successful in passing 6.25 into 10 raised to 18 electrons per second. So I hope you understood this concept of current. So we will meet in lecture 3 with some new concept. Thank you.